Hello everyone, welcome to the first lecture of carbon materials in manufacturing. Okay, now before we start talking about carbon materials specifically, in this lecture I'm going to discuss briefly about what are materials and what are the properties of the materials that we need to know before we start thinking of manufacturing something. What is manufacturing? Manufacturing is just making something. And for making something you need to know certain fundamental properties of the material. What are these properties? So let's think about, let's take an example of an iron material, cast iron, any kind of iron, steel, also alloy. Now you want to make some shape out of it and you want to perform casting. Now, what do you need to know when you perform casting? Number one, you need to know what is the melting point of your material? What kind of crystal structure does it have? Will there be any phase transition change in the crystal structure when you heat it to, a very high temperature? If it is a steel, then what kind of steel it is? What is the hardness of the steel? So all of these properties, what kind of defects do you have? All of these things you need to know, and also you need to know the properties of the material in order to understand the application. Why are you making certain structure using iron? Maybe because of its mechanical strength, maybe because of its electrical conductivity, maybe because of certain other properties. So all of these things you need to know. And how do we learn about these properties? Okay, now think about carbon. The very fundamental thing about carbon, something very important for this entire course, is that carbon is not one unique material. Or even, so it is an element, it's a unique element. Atomic structure remains the same, but you have several different carbon materials, and that is because the definition of materials itself is a very general definition. Any any element or any alloy or any compound can be called a material as long as you have a uniform structure at a molecular level. So this means that if you take two samples of the same material, you should be able to get the same properties. And that is when you call it a material. And especially when it comes to manufacturing techniques, then the material term is used in a very very broad way. Everything is called a material. Anything tangible is a material for manufacturing purposes. Okay, so carbon is also then can be called one material, but the point is that carbon it can have various crystal structures. It can also have some mixed crystal structures. Or you probably know about hybridization. So I know that in the high school textbooks you learn very fundamental things about hybridization. And when I was in high school, I only learned about graphite and diamond, but I understand that now they have also included a short write-up on fullerenes. So this is very good. Now we already know, we are familiar with the materials, and then we are going to build upon that. But anyway, I'm going to also discuss some very fundamental aspects. The point is that based on these hybridization states, carbon can actually take different physical forms. And you can also do different manufacturing processes. So for example, you can make fibers out of it, or you can make nanoscale materials out of it. In fact, many of you, when you took this course, you must be thinking only in terms of carbon nanomaterials. The first carbon material nowadays that comes to people's mind is graphene. And then you also think about carbon nanotubes, and then you might think about fullerenes. These are the carbon materials that are very extensively studied nowadays. So for research purposes, they are very important. But for industrial purposes, for manufacturing purposes, still the good old-fashioned carbon materials like graphite and glass-like carbons and activated carbons, these still remain very important. So what we need to know is we need to know about all of these materials. And what we need to know is how can we change the properties of these materials? Can we also design a new carbon materials? Can you come up with a new carbon materials? The answer is yes, if you understand your material at number one atomic, number two molecular, and number three crystal level. So the carbon atom remains the same in all carbon materials, irrespective of what is the scale at which you're using it or at which you're manufacturing it. Carbon atom and its properties remain the same. What is different is the molecule, and then accordingly the crystal structure may differ. What is a molecule? When you have a lot of atoms together and they form bonds, and then that is how you get a larger unit which is more stable. In the case of carbon, you can have massive sheet-like molecules, or you can have sphere-like molecules. You must have heard of C60, which is the Buckminster fullerene. This is one molecule. So in the case of carbon, these molecules can also be very interesting. And of course, the crystal structure, you know about diamond and graphite. So you know that crystal structure is dependent, it is determined by the hybridization states and the shape of the orbitals. We are going to discuss all of these things. But the point is that you can have, completely different properties just because of this hybridization and this slight change in the crystal structure. You can also have very different mechanical properties. A certain carbon form will have a slip plane. On the other hand, another carbon form will not have a slip plane. In that case, you can have very different mechanical properties as well. So these are the things. Once you understand the carbon atom, and then you understand carbon at a molecular level, what kind of molecules are actually possible, or energetically favorable. And then, of course, based on that, then you understand the crystal structure. So these are the things that we learn about, not just carbon, but for any material when we talk about manufacturing processes. Okay, what is an atomic structure? Very simple. You know that there is an atom, it contains electrons, and there is also a nucleus. And nucleus has protons and neutrons. Okay. There are many models so for example, you must have learned about the Bohr's model, where you have a circle, everything is spherical and circular, and then you have electrons orbiting around the nucleus. That is a very good representation for an easy explanation, especially in school, but that is not really correct. So you don't have the orbitals are not really the orbits or the path that electron takes around the nucleus. That is not the case. So that is also one thing you need to forget about these models where electrons are orbiting around a certain or they take a certain let's say circular path. That is not the case. What is an atomic orbital? Orbital is just a region in space where you have the highest probability of finding an electron. So these are basically probability distributions. Okay, so this is and we mathematically derive the shapes of these orbitals by solving the Schrodinger equation for hydrogen atom. So we just take a single electron system, hydrogen atom, because that's the easy way of solving the Schrodinger equation. And then based on that, we know that there are certain mathematically, we derived shapes where you can find the electron. There is no real concept of the path that the electron will take. Actually, in the case of electron, it's here, and after some time it's here, and then it's here, and then it's here. We just really don't know how did it reach from one place to another place. Okay, we don't know anything about the path of the electron. We also don't know anything about the shape of the electron. It can be just some crazy shape. We have no idea about it. In fact, if you're more interested in this these topics, then you can probably go through some of the NPTEL lectures on quantum mechanics. But the point is that electrons, so these are just probability distribution functions, atomic orbitals. Okay. Now, we will also maybe talk a little bit more about the orbitals when we talk about hybridization, because that is this is the easy way of understanding. When you understand the orbital only, then you can understand hybridization. Okay, and especially in the case of carbon, because you may have some strange hybridization states which are SPX. So we are also going to learn about them, and then we will also, that's where it becomes very important to understand that these are just discrete probability density functions. Okay, now we come to the molecular structure. What is a molecular structure? When you have two or more atoms coming together and they are forming a bond. Why do they form a bond? They basically merge their energy levels. So the orbitals are energy levels. They merge them and they form a what is known as hybrid energy level in some case. And if whether or not they form this hybrid energy level, they do come together, and that gives them a more stable state. That is the reason you form a bond, because then you have a more stable overall geometry. And that is why you don't, it's not necessarily just two atoms, it can be more than two, it can be 60 atoms also. If that is what gives it a more stable geometry, then you can have these bonds and then you can form molecules. Now, of course, you know that what are elements and what are alloys and what are compounds. So here, this is a crystal structure of one element, and this is a crystal structure of one compound. So now coming to the third level, that is the crystal structure. It is something that is, how the atoms are organized. When they form a molecule, it's typically not one single molecule. There may be, millions of such molecules. And then this entire molecular geometry somehow needs to organize itself again to get an overall stable geometry, energetically favorable geometry. So everybody wants to minimize their energy. But you want to sleep. Sleeping is when you're in your minimum energy state. You're not really very sad, you're not happy, you're not angry, you don't have any emotions, you just, that's your minimum energy state. And that is what everybody wants to get. And similarly, the molecules and crystal structures, every chemical structure also wants to attain the minimum energy state. And that is what we also call thermodynamically favorable state. And that is the direction it takes. So it organizes itself. So all the atoms and molecules, they would arrange themselves in such a way that they try to get that minimum energy state. And sometimes that is why you will have these repeating units and very regular structures, which you would call crystal structures. And interestingly, there are certain classes that actually classes of crystal structures that can actually explain or accommodate pretty much all the elements, all the materials. Okay, so this is a crystal structure. Now, crystals, are they always 3D crystals? So whenever we talk about crystal structure, what comes to our mind is a cube. Because we have the face-centered cubic structures, we have base-centered cubic structures. So what often comes to our mind is something which is 3D. Even when we talk about a hexagonal crystal, we are thinking in 3D, right? But it's not always the case. So let's say here I have drawn a crystal. There you have like lots of cubes stacked on top of each other, so you get a 3D geometry. But if I just remove one layer, the one that is shown with the darker color, if I just remove this one layer, then that becomes my 2D crystal. Crystal is nothing but an arrangement where you have repeating units. You can also have that in 2 dimensions. So these are the kind of materials which are called layered structures. And these kind of crystals are known as 2D crystals. Okay. Now you can also have a third thing which is known as semicrystallinity. So now it gets a little more not complicated, but it's a mixture of crystalline and non-crystalline materials. Something called semicrystal. So you have polymers. So this is an example. You know about polymers. You know that they contain these chain-like structures. Some polymers may contain sheet-like structures as well. And here and there, occasionally, some part of them has this arrangement or certain type of arrangement, layered arrangement, let's say, certain parts. But you see on both sides of this, what I have made, the crystal geometry, both sides are then random. So certain parts in the material will have this crystal structure or certain arrangement. And these crystallites, the little parts where you have the arrangement, you will call them crystallites. And these crystallites, however, in the bulk material, they are randomly oriented. So not all crystallites are then, arranged on top of each other or something like that. Then these crystallites are randomly oriented. So these kind of materials are known as semicrystalline materials. Okay. Now, a single crystal can be just a few nanometers long, or in terms of size. Or sometimes you can even have several centimeters long single crystals. So for example, when you manufacture silicon, you actually have single crystals that are several centimeters long. So you can have crystals with or without defects. You can have crystals which are small, which are large, and different crystal structures are what basically determine the properties of a certain material, at least when it comes to the manufacturability of that material. Okay, so now I will talk about, so we talked about crystal structure, but what is not crystalline? So what are the things that are not crystalline? Are they always amorphous? So whenever you learn about crystalline materials, You learn about there are some materials that are crystalline with a nice order and the others are amorphous. If I tell you how to define an amorphous material, that's not easy. You would think it's very easy, but it's not really easy, because you can say that something that shatters on breaking is amorphous, but that's not completely correct. Okay, so 3 definitions: amorphous, crystalline, and disordered materials. So amorphous and crystalline you know, disordered you don't. Okay, so is crystallinity first of all a physical property? Yes and no. It is a physical property because what you see in the, it determines a lot of properties of the material, the physico-chemical properties, but as such it is an arrangement. So you can say this is a physical arrangement of atoms, but that physical arrangement is sort of defined by the chemical properties of the material, by the attractive forces that the atoms have with each other, by the nature of bonding. So it is both a chemical and physical property, but it definitely influences the chemical behavior of a material. It definitely influences the electrical, thermal, all sorts of behavior of the material. So as such you can say it is a physical arrangement, it's a physical property, but everything is guided by the crystal structure of a material. Okay, so this means that you have certain order. Crystallinity means you have certain order in the material. Now sometimes what you may have is, you will say that this material has certain fraction of crystallinity. What is crystallinity? Crystallinity means the property that you have, you are a crystal. That is your crystallinity. But now certain materials may not be completely crystalline, they may not be a single crystal. Single crystals, large scale single crystals are relatively rare. Even in nature, when you mine something, large scale single crystals are rare. But what you can have is partial crystallinity, or a certain fraction of the material which is ordered, like you also saw in the case of semicrystalline materials. But also you can have this kind of order in elemental materials, not just in polymers. You can have, not even when you, so in the case of semicrystalline polymer, you saw that there are chain-like molecules, but you don't need to necessarily have chain-like molecules to have fractional crystallinity. So some part of your material is crystalline and the rest is, what is it? Well, let's just call it non-crystalline. The term amorphous needs to be used very carefully. Okay, now so crystalline material has a well-defined order. Let's see here I have shown a picture. What is this picture? There are these lines. What are these lines? These lines are basically planes. These are crystal planes. So this is like a cross section of your crystal. And these lines are actually, then they are going into the computer screen, so they are like planes. Okay, so this is a crystal. You see that this is there is very nice order. You have lines with well defined distance between them. So this is your crystal. Okay, now the second type of material is the amorphous material. So as I said, the definitions of amorphous that you've learned, basically they all start from this, that the material is it shatters on breaking. A lot of things can shatter on breaking. Even if you have a polycrystalline structure, polycrystalline means a lot of crystals. You have the material which has a very high crystallinity, which maybe more than 90%, in terms of crystallinity if you measure it. But each crystallite is very small. Crystallites are then on each other, they are randomly organized. They are not, one crystal is not exactly on top of another crystal or not exactly in the same direction. You can have very random directions of your crystallites. Even that will physically break. If you drop it, it will shatter. It will not break according to a crystal plane, which is the property of a crystalline material. You know that the metals which are crystalline, they have a certain plane. If you break it, they will break along that plane. But amorphous materials, so how do you define amorphous materials? Amorphous materials basically have variable bond lengths between any pair of atoms. Okay, so this is like the formal definition, which you have completely random bond lengths. So if I have 1000 carbon atoms, then carbon 1 and 2 have certain bond length, 2 and 3 have something else, 3 and 4 have something else, and so on. Maybe there is some, the same bond length carbon number 1 and 2 have, maybe carbon number 67, 68 also have the same bond lengths, but overall what you get is a range of bond lengths. Then you call it an amorphous material. So there is no order whatsoever. So if you take a picture of an amorphous material, I don't know if it's very clear from here, but what you see is like a gray area. You don't really see, because when you take pictures at this scale, you're using electron microscopy. So what you get is this kind of random picture where you cannot really differentiate. You cannot say this is where my atoms are and this is where they are not. So this is an amorphous material. Now what is the third type of the material? Disordered materials. So disordered, as the name itself suggests, they are not ordered, so they're definitely not crystalline. But what you have is a short range order. What does it mean? You have crystallites, but they are very short. So there is an order, but only for some time, only for a very small distance. So this is called a short range order. So you have crystallites distributed through the material, and they have certain order, so that you may increase that order by, for example, increasing the heat treatment temperature. We'll come to it. For carbon materials, this is very important. So you see in this picture, now I have taken the picture from the crystal picture and the amorphous picture, and this is like a mixture of the two. So you have tiny little crystallites distributed inside an amorphous matrix. And these crystallites, now they may or may not be attached to each other. They may not be connected to each other. If you, somehow by tuning the manufacturing process, if you can keep on increasing the size of these crystallites, at some point they will touch each other. Then you call it a percolation point. Percolation means, when you have this network formation inside a material. Once you have the network, what is going to happen is you're going to have electrical conductivity in the material. Because you know that crystalline materials, it's not the case with all crystal structures. For example, diamond is crystalline, but it's still an insulator. But typically for many metals, if you have a crystalline structure, then, and if you do have free electrons for electrical conductivity, then if it is crystalline, it will have higher electrical conductivity, because there is a nice path for the electron to flow. But in the case of amorphous, you will not have that kind of electrical conductivity. Disordered materials will be somewhere in between, especially when they have this percolation, when they have a network of these tiny crystallites. Then electron can find a path. Electron can definitely propagate. You will have electrical conductivity, maybe also thermal conductivity, other properties. But if you drop that material, it's going to shatter on breaking. So you don't call it crystalline, but just because it shatters, you also don't call it amorphous. You need to now understand the material at its atomic and molecular level and crystalline level to say that this is neither amorphous nor crystalline. This is a disordered material. And a lot of bulk industrial carbons, they are disordered materials. So I think this is my personal opinion. In the case of carbon, if you don't know the exact structure, microstructure of the material, then just rather use the term disordered rather than amorphous, because carbon almost always has certain short range order. Okay, so we'll come to it. Okay. Yeah, so most of the carbon materials that are based on graphite, and based on graphite, I mean that you have sp2 hybridization, at least to some extent. Not all the atoms are sp2 hybridized, but you do have sp2. This is a primary hybridization state in your material. In that case, I will call it graphite-like material, or sp2 carbon materials. Most of these sp2 carbon materials, if they are not perfect graphites, in that case, they are often physically amorphous. Now coming to the microstructure of a material. So this is yet another important definition. The term so now the pictures that I showed you, these schematic diagrams, what do they indicate? What they indicate is the microstructure of a certain material. Microstructure basically would mean how does a material look like at a crystal level. But this is not the formal definition of microstructure. What do you see in those? You saw the crystalline and amorphous phases. Crystalline and amorphous are phases of the materials. We will also talk about them when we talk about the phase diagram. So crystalline amorphous phases you saw, but you also saw how how are they associated with each other. So how much crystallinity you have in a material, that you can see when you see those kind of pictures where you see the microstructure of the crystal. If you have certain defects, you can also see the defects. Okay, for example, in the case of carbon, if you have non-six-membered sheets, then you will see, maybe you will not see the individual atoms, but you will see that, okay, these are not perfect crystals. There is a certain waviness in those crystals, which may have been because of the defects, because of certain, so there is some disorder in the ordered material also. So these kind of things you can see when you see the material at that scale. Then how do you actually define your microstructure in any material? When you can see or you can analyze the phases plus the defects plus any residual stress, all together you call it the microstructure. Now this term is a little bit unfortunate because it is called microstructure, but in the pictures now now we have very advanced electron microscopy techniques. We have transmission electron microscopy, for example. You can have very high magnifications. You can see the material very much at the nanoscale. Even some very advanced TEMs will give you even atomic scale images. So you can definitely see the pictures of that scale, but you don't call it nanostructure. You still call it a microstructure, because the term microstructure was coined when anything that was too small was just called micro. Even now we use the terms like micromanagement, micro this, micro that, which basically just means very, very small scale. So same thing for microstructure. So, but you need to understand that when you're talking about the phases plus defects plus residual stress, and phases can be crystalline, amorphous are also phases. So that is how your materials microstructure is defined. If you want to know more about the material and microstructure and these very fundamental properties of materials, then I strongly recommend this lecture by Anand Subramaniam. That's for your further learning, because in this course we will not be able to talk about all the aspects of materials crystal structure. We'll mainly talk about carbon materials. Okay, now because of the fact that microstructure it has the term micro in it, sometimes it's also confused with microscale structures. So nowadays we do all this micro fabrication and nano fabrication. We make devices even that are extremely small, that are in the micro scale, micro domain. Let's say micrometer is 10 power minus 6 meter. You know that. So these micro scale structures are also sometimes, they can be called microstructures because they are micro scale structures. But don't get confused. For a material scientist, microstructure is the phases, defects, residual stress. But for a microsystems engineer or somebody who makes micro scale devices, then it can be also micro scale structure. So what we are going to do in this particular course, in order to avoid any confusion, when I talk about micro scale structures, I'm going to put this hyphen, micro dash structures. Then we are talking about a device, and when I write one single term microstructure, then we are talking about, well, microstructure. Okay, now yet another thing is nanoscale structures or nano materials. You must have heard the term nanomaterials. What is so special about nanomaterials? Isn't every material nanomaterial? Because every material has some nanoscale units which are the fundamental or the building blocks of that material. Everything can be called a nanoscale material. So what is the special thing about these nanoscale materials? Okay, now when we talk about nanocrystals, let's talk about the crystalline materials that are crystalline at nanoscale. Then they are pretty much like what you had in a disordered carbon material or disordered material that I showed, except the fact that they are not inside an amorphous matrix. They are just there. They are just present. So yeah, this image, nanocrystal powder. So this is where you see that you have these nanoscale crystal structures. It's important that they are in the nanometer scale. And then, however, they are each one of them is randomly oriented, and in bulk form what you will get is a powder. It can be a 2D crystal, it can be a 3D crystal, any kind of crystalline structure which is very well defined. So we intentionally made it. So this is also the overall idea of nanotechnology, is that, okay, there were things in the nanoscale, always there have been biological things, and everything has an atomic structure. So we do have things that are in the nanoscale everywhere around us. But when we intentionally design a certain type of crystal or structure, at a nanoscale, and then we are able to get what we designed. Then we call it technology. Then it's a technology. Also, the fact that we are able to characterize those materials. We are not just characterize, but we are able to utilize the properties of these nanoscale materials for technology, for technological applications. That is altogether nanotechnology. So nanoscience is about understanding the properties of the material at nanoscale, and nanotechnology is when you utilize these nanoscale materials, let's say nanocrystals, for any technological applications. So for example, making devices, making coatings, making a lot of functional structures and so on. Okay, so nanocrystals in bulk form. So when you purchase a bottle of a nanocrystal, then you're going to get a powder. Now, if you look at that powder inside a very high magnification microscope, then you're going to see these nanoscale crystals. Okay, so typically when you want to do manufacturing with nanomaterials, what you're going to do is you need to bind them together. So you will not use a single nanocrystal of this kind for a device. You can. There are examples. This is where the research is moving forward. How can we utilize single nano structures for technological applications? But in general, a lot of manufacturing is still done by mixing these nanocrystals or the powders into a binder, bind them and make something out of it. Then also you can get the functionalities, if not all of them, at least a lot of them, the functionalities of your nano material that you designed and prepared. Okay. Now you can consider them crystalline or amorphous. That I leave it up to you, because you see what it is. It is crystalline at nanoscale. We prepared something that was crystalline. Because it is crystalline, it's going to give you beautiful properties of a crystal. It's going to give you whatever electrical conductivity you want. But in fact, at nanoscale, the properties become very much more interesting. Now you see, nanocrystals will not have defects. Large scale crystals, or if you're doing manufacturing with cast iron, the actual manufacturing materials, they have a lot of defects. We know that. But nanocrystals, well, the defects will anneal out. The defects will leave the material. The entire crystal is so small. Where will the defect? If there are defects, then this makes it a very high energy structure. It will try to minimize its energy, get rid of the defects. So many properties of the materials change at the nanoscale. And that's why they're very interesting materials. The point is that, do you call them crystalline or you call them amorphous? If I take the bulk powder, like I said, I purchase a bottle of nano powder, nano material, then I get a powder, then that powder in bulk is amorphous. Amorphous, physically amorphous, that shatters on breaking. If I also mix this nano powder into a binder, altogether that structure will also shatter on breaking. But the properties that you get, they are from the crystal. So you can call them crystalline, you can call them amorphous, or you can call them, nanocrystals. So better to call them nanomaterials and nanocrystals. Okay. Now, yeah, there are like I said, that you can do manufacturing using binding. So this is a bottom-up manufacturing approach. Bottom-up means when you add things one on top of another. You also call it additive technique. And top-down approaches means when you remove material from, you take a big block and whatever is the undesired material, then you remove that. So those are called top-down processes. So often large-scale manufacturing processes are top-down because, if you start making things, then it's going to take a lot of time. But there are also examples of large-scale bottom-up, manufacturing. You would not call it manufacturing, let's say construction. When you have a building construction, then you have bricks one on top of other. That is bottom-up process. So also in the large scale, you will have certain bottom-up processes for making things, whether you call them manufacturing or not. But typically for industrial, tool manufacturing and so on, you will use top-down approaches when it comes to large-scale production of something. But so this is the idea of a material, and these are the things we are going to learn about. Carbon materials. From next lecture onwards, we will talk specifically about carbon.